All right, so in section 9.3a, this one's called the integral test for convergence. Not everybody calls it the integral test for convergence. Some will just call it the integral test. But this is one of the first big tests that we use. We've already talked about the nth term test for divergence. We talked about geometric series and how you can check to see if those converge based on the R value. So we're going to discuss integral tests. Now let me give you the definition of the integral test. This actually comes out from a theorem. So this would be theorem 9.10, the integral test. And this is what it says. And it has some prerequisites. So you got to make sure all these prerequisites actually hold true before you can actually use this test. So it says if f is positive, continuous, and decreasing. So continuous, positive, continuous, and decreasing for all x greater than or equal to 1, then if a sub n is the same as f of n. In other words, if you can rewrite the series as a function, in other words, you're just changing variables, so it's not a big deal. We get the following. The sum as n goes from 1 to infinity of a sub n and the integral from 1 to infinity of f of n, f of x dx, either both converge or both diverge. So they're either going to both converge or both diverge. So in order to understand this integral test theorem, you got to make sure, like I said, there's three prerequisites. You got to make sure that the function is positive, or the sequence at least is positive. You want to make sure that it's continuous. And a lot of times you can just graph it to see it. And you also want to make sure that it's decreasing. Okay, it has to be getting smaller and smaller as it moves to the right side. So as the function keeps going towards the right, it must stay above the x-axis. It must not have any holes or breaks or anything like that. And it has to be getting smaller and smaller. And if those three things are true, then we can check for the convergence of the series by checking to see if the integral actually has an answer. And if the integral actually has a constant value, then we say it converges. And if the integral converges, then the series will converge. But if the integral diverges, then the series will diverge. So let me show you maybe 2 or 3 examples on this. Okay, so let's see. Example number 1. So they're going to want us to apply the integral test to the series and the series is the sum as n goes from 1 to infinity of n over n squared plus 1. So our a sub n is n over n squared plus 1. So in order to do the integral test, they are telling us to apply it. So in other words, they're already assuming that we're going to be checking to see if it's positive, if it's continuous, and if it's decreasing. Okay, so you should be able to tell that this function is never this function will never be negative, because since we're going from positive 1 to infinity, no matter what numbers for n we use to plug in, it's never going to become a negative value. So it is positive. It's also going to be continuous because there's no real number that will make the denominator equal to 0. So that's not a big deal. And then the fact that it is an n squared plus 1 in the denominator, that means it's increasing faster in the denominator than the numerator. It is going to be a decreasing function. So all three of those things apply. So all I have to do is check the integral for this function and see if it actually has an answer or not. So I'm going to integrate from 1 to infinity of x over x squared plus 1 dx. Now, I know that I can do u substitution for the bottom, an x squared plus 1, but my derivative will be a 2x. So let me just kind of apply this really quick so you can see what you would have to do. We're going to let u equal to x squared plus 1, so du is 2x dx. Now, you'll notice I don't have a 2 up there, okay? So in order to make this thing kind of work out, what I could do is just divide by a half du, and that'll give me an x dx, so that should be good. Now let me rewrite this thing here first off. So I see that I have 1 to infinity. This is an improper integral, so I'm going to take the limit as b approaches infinity from the integral, of 1 to b of x over x squared plus 1 dx. Now this right here can be rewritten as the limit as b goes to infinity of 1/2 the integral of, now I'm going to do my u substitution here, so this becomes a 1/2 du and then a 1 over u right there. So limit as b goes to infinity of 1/2 of the natural log of the absolute value of u, of course plus c, but I'm not going to put that yet because I'm about to substitute back in my u value. So that's a limit as b goes to infinity of 1/2 of the ln of the absolute value of x squared plus 1 from 1 to b. Now if I plug that stuff in, I get limit as b goes to infinity of 1/2 of ln of b squared plus 1 minus ln of 1 squared plus 1, which is the limit as b goes to infinity of 1/2 of ln of b squared plus 1 minus the ln of 2. So apply the limit to it, and we're going to get 1/2 ln of infinity squared plus 1 minus ln of 2, which is basically half of infinity, which is infinite. Now, since the limit does not converge, because the limit went to infinity, that means it's diverging. Okay, I'm going to put right here, diverges. Since the limit diverges, then that means the series diverges. That's what the integral test is supposed to tell you. So I'm going to write, since the integral from 1 to b of x over x, I'm sorry, not 1 to b, 1 to infinity, of x over x squared plus 1 dx diverges, then the series as n goes from 1 to infinity of n over n squared plus 1 also must diverge. So that's the answer for that problem. Remember, the integral test basically states that whatever happens to one must happen to the other. So if the integral diverges, the series diverges. If the integral converges, the series converges. Now, if you wanted just to double check the function before you actually started doing any of the work, like I said, you could graph it. So notice x divided by x squared plus 1, and just have it graph it. I know it's kind of hard to see, but let me zoom in a little bit more. So zoom in right to the center. You're going to notice that the function itself, notice from 1 to infinity, it's above the x-axis, it is decreasing, it will be continuous. It's basically going to try to approach zero as close as possible, but it's never going to get there. So just wanted to show you that that was the case. Now there's going to be another function that I'm about to do right now for you guys. I want to show this one to you guys. That's 1 divided by x squared plus 1. There's actually going to be an arctangent when I integrate, but look at the graph for this one. Okay, so as it starts going from 1 to infinity, it starts to decrease. It is continuous. It is positive. It's never going to go under 0. So I can kind of tell that this function is going to be okay for me to integrate as well using the integral test. Now let me close this up. I'll maximize my other window here. And let's do the second example. So example number 2. We're going to apply the integral test. Two. And here is the series. The sum as n goes from 1 to infinity of 1 over n squared plus 1. So this is the one that we just saw on the graph. It does fit the definitions of a decreasing function, a positive function, and a continuous function. So what we're going to do is integrate from 1 to infinity, 1 over n squared plus 1. I'm sorry, not n, x squared plus 1 dx. Now, first off, we have to apply the limit as this is an improper integral. So it's the integral from 1 to b instead, 1 over x squared plus 1 dx, as b approaches infinity. Now, this definition fits the definition for an arctangent, 1 over x squared plus 1, where our u value is x and our a value is 1. So this basically integrates to the following. The limit as b goes to infinity of arctangent, or if you want to write tangent inverse, I'd rather write tangent inverse, to be honest with you. So tangent inverse of x from 1 to b. Now we plug in our values. So limit as b goes to infinity of tangent inverse of b minus tangent inverse of 1. Now I do know that the tangent inverse of 1 is 45 degrees. So I'm going to put that right here. That's pi over 4. Okay, now if I apply the limit, I get tangent inverse of infinity minus pi over 4. Well, if you think about tangent inverse or your tangent function, there's only one angle that makes it go to infinity, and that would be a pi over 2. So pi over 2 minus a pi over 4 equals to a pi over 4. Notice this is a constant value, so we say that this integral does converge. It actually has an answer. So for my solution, I'm going to write, since the integral from 1 to infinity of 1 over x squared plus 1 dx converges, then the sum as n goes from 1 to infinity of 1 over n squared plus 1 also must converge. And again, this is by the integral test, okay? Because of the integral test, we're able to say that that series can converge. So let's just do one more example of this type, and then I'll let you guys start doing your work. Let's see. So example number 3. Now, they want us to use the integral test to determine convergence or divergence. Okay, so use the integral test to determine convergence or divergence. So this problem has the following. It says ln of 2 over 2 plus ln of 3 over 3 plus ln of 4 over 4 plus ln of 5 over 5, etc. So your job is to rewrite this as an actual series. So first, let's write it out as a sequence. You can see that the ln of 2 over 2, 3 over 3, it's the same. So this is most likely an ln of n over n. So this is most likely my a sub n. So I'm going to start writing this out as the sum as n goes from 1 to infinity of ln of n over n. That's going to be my series. But if I want to check to see if that series converges or diverges, I'm going to have to check to see if the integral from 1 to infinity of ln of x over x dx actually converges or diverges. So again, since this is an improper integral, we're going to take the limit as b goes to infinity from 1 to b of ln of x over x dx. Now I'm going to use a u substitution. So let u equal to ln of x. So du is 1 over x dx. And that fits perfectly because 1 over x dx is right here. And of course the ln of x is up on top. So this becomes the limit as b approaches infinity of the integral from 1 to b of u du. So let's integrate that. So the limit as b goes to infinity of u squared over 2 from 1 to b. Let's apply the fundamental theorem of calculus. So that's going to be b squared over 2 minus half. And if I apply the limit, I basically get infinity squared over 2 minus half. Well, infinity squared is infinity. You divide infinity by 2, you get infinity. And if you just subtract a half from infinity, it's still infinity. So this thing diverges. Okay, so the integral diverges. And if the integral diverges, then so must the series. So since the integral from 1 to b of ln of x over x dx diverges, then the series as n goes from 1 to infinity of ln of n over n also must diverge. Remember, the main idea behind the integral test is whatever one thing does, the other must do. So whatever the integral does, the series must do. So if the integral diverges, the series diverges. If the integral converges, then the series must converge. So I'm going to give you guys a small assignment to do for today, and then tomorrow I'm just going to give you guys a book day, meaning continue your homework, also continue with any past homework that you need to do. So I will be collecting homework, I think after section 5 or 6. I can't remember which one, but we're kind of getting there. We're in section 3 right now, so make sure you guys are keeping up with that. So your homework assignment is the following. All right, so let's see, homework, page 622, numbers 1 through 8. what else? 11 through 13. And 20 and 21. So that's your assignment. You guys should be getting started on that right away. Again, tomorrow you guys have a book day, so make sure you guys bring whatever it is you need so that you guys can just do work in class. And then when I get back on Wednesday, we'll talk about the P-Series test. So get to work.